Hello, ladies and gentlemen, welcome back to our channel. Today we'll be talking about dimension analysis in physics. We'll be looking at dimension analysis. A lot of people have made a lot of requests on dimension analysis. We want to break it down now. What do we mean by dimension analysis? Dimension analysis simply means expressing physical quantities in terms of the basic quantities. Expressing physical quantities in terms of the basic quantities. What are the basic quantities? The basic quantities are mass, length, and time. Mass, length, and time are the basic quantities. If you express every physical quantity in terms of mass, length, and time, what you are doing then is referred to as dimension analysis. In dimension analysis, mass is going to be represented as M, capital M. Length is going to be represented as L. Time is going to be represented as T, capital T. What is the implication of this? In all the answers and derivations you're going to get in dimension analysis, it is going to be expressed as M, L, T. M, L, T is going to be the end product of all your derivations, calculations, or workings in dimension analysis. All the answers you're going to get in dimension analysis is going to be M, L, T. Here M represents the mass, L represents the length, T represents the time. There are a lot of reasons why dimension analysis is very, very important. That is to say, the importance or relevance of dimension analysis cannot be overestimated. One of the most important reasons is that dimension analysis is used to verify the validity of a physical formula or expression. Using formula, you can use dimension analysis to prove whether the formula is correct or wrong. That is to say, the plausibility of an expression can be determined using dimension analysis. You can also use dimension analysis to express the relationship between two or more variables. Similarly, you can also use dimension analysis to give dimension to a dimensionless quantity. When you're being given a dimensionless quantity, with the help of dimension analysis, you can now give dimension, you can now prescribe and give unit to a dimensionless quantity. Now, how do we do this? Let's talk an example. Yes. The following in dimension. We're going to use these few examples to illustrate dimension analysis. We're going to use these few examples to illustrate dimension analysis. First of all, area. Area. What do you mean by area? Area is defined as length times length. In other words, area is length times length. So if we want to express area in dimension, first of all, we should think of the derivation of what? Area, which happens to be length times length. In dimension, length is represented as what? L. The other length will be represented as L, which means in dimension, length area is going to be length times length, which will give me L square. So L square becomes the dimension of area. L square becomes the dimension of area. Since the dimension of length is L, the other length is also L. Since area is length times length, L times L will give me L squared. Okay? The second example here is volume. Volume is defined as length times length times length. Length, as we described earlier, is represented dimensionally as L. So since we have 3 of the length, we're going to have L times another L, giving us cubic length as the dimension of volume. Okay? Since we have looked at this, let's proceed to the other ones. The third one I have there is density. Density. Density is defined as mass per unit volume. Density is described as mass per unit volume. Density is mass over volume. Mass over volume. So density is described as mass per unit volume. So since density is described as mass per unit volume, To find the dimension of density, what will be the dimension of mass? We already know that the dimension of mass is capital M over the dimension of area, as earlier said, is dimension of volume, as earlier said, is LQ, and this will give us M over L raised to the power of 3, and this is written as M L raised to the power minus 3. Remember that this is gotten from negative index from the laws of indices. Don't forget that in mathematics, the laws of indices, a raised to the power minus s is equal to 1 over a raised to the power s. That is the negative law of indices, which states that if the index of your number is negative, then the result is the reciprocal of the number raised to the power of the positive index. That is to say, if I have L raised to the power minus 3, it is the same thing as 1 over L raised to the power 3. Therefore, M L raised to the power minus 3 is the same thing as M over L raised to the power what? 3. So subsequently, anywhere we have something like this, it implies M L raised to the power minus 3. Similarly, assuming I have M L raised to the power 2, it will give me M L raised to the power minus 2. M over L will give me M L raised to the power minus 1, and so on and so forth. Okay? The next one we have here is, the fourth one we have is velocity. The fourth one we have is velocity. Velocity. What is velocity? Velocity is defined as rate of change of displacement with time. Velocity is described as the rate of change of displacement with time. That is to say, velocity is displacement over the time taken. Now, dimensionally, displacement is a measure of distance, which is a measure of length. So, dimensionally, displacement is written as L. Over time, dimensionally is written as what? T. And this will give us LT raised to the power minus 1. This will give us LT raised to the power minus 1. Okay, the next one I have here is force. Force. What is the dimension of force? Force is defined as mass times acceleration due to gravity. Force is defined as mass times acceleration due to gravity. Okay, the next one is more. Force, mass times acceleration due to gravity. We already know the dimension of mass. We don't know the dimension of acceleration. But we know that acceleration is rate of change of velocity with time. Acceleration is the increase in velocity with respect to time. So velocity over time will give us acceleration. The dimension of velocity is LT raised to the power minus 1. Dimension of velocity, you already know how we got this. Dimension of time is what? T. Therefore, we can practically say that dimension of acceleration will be LT raised to the power minus 2. What does this imply? We have L over T being velocity, all divided by T being time. So L over T, if I change this division to multiplication, I will take the inverse of the divisor. This will now give me L over T squared. L over T squared is the same thing as LT raised to the power minus 2, which happen to be the dimension of acceleration in case it's being asked. So the dimension of acceleration is LT raised to the power minus 2. Substituting it here, the dimension of force will now be mass, which is M, times acceleration, which is LT raised to the power minus 2. And this will give me MLT raised to the power minus 2. As dimensionally force. That happens to be the dimension of force. Okay, the sixth one we have on the list of the examples is work, which I just explained. Work. Work is said to be done when a body moves a distance in the direction of an applied force. Work is said to be done when the body moves a distance in the direction of applied force. In other words, work is force times the perpendicular displacement. So force times distance will give us work. Earlier on, we have gotten the derivation, the dimension of what? Force. So force dimensionally is expressed as mLT raised to the power minus times distance is length, which is what? L. If this is so, we are going to have m. There is no other m over here, so we still have one m, l, and another l. This is just like saying l times l. What would it to give us l squared? So we are going to have l squared t raised to the power minus 2. This happens to be the dimension of work. Note that the same thing is also the dimension of energy, because energy is dimensionally equal to work. Work done is a direct function of the energy dissipated. This implies that if you put in 20 joules of energy, you're going to produce 20 joules of work. So energy and work is dimensionally the same thing. Just like speed and velocity is dimensionally the same thing. Just like moment and work is dimensionally the same thing. Okay? The next thing we have there is momentum. Momentum is defined as product of mass and velocity. Momentum is mass times velocity. Momentum is mass times velocity. The dimension of mass is capital M times the dimension of velocity is Lt raised to the power minus 1 as earlier gotten. This will give us mLt raised to the power minus 1. mLt raised to the power minus 1. I have pressure here. Pressure is force over area. Force over area. Pressure is force over area. Pressure, repeat, is force over area. Now, dimension of force, we already got dimension of force to be mLt raised to the power minus 2, all divided by the dimension of area, which we said earlier that it is L squared. Now, working on this, we have M here. L divided by L squared. If you break it down this side, we have L over L squared. L divided itself will give us 1. This divided itself will give us 1 of the L, which means that we are having 1 over L. Since L squared is what we have, just breaking this down again, L over L times L, which means this L can cancel one of this L, remaining us with 1 over L, which means we are going to have 1 over L is written as L raised to the power minus 1, which means here I'm going to have L raised to the power minus 1, T raised to the power minus 2. So this is the dimension of pressure. This is the dimension of pressure. The next one I have as an example here is impulse. Impulse. The ninth one is impulse. Impulse is product of force and time. Impulse is force times time. Dimensionally, force is expressed as mLt raised to the power minus 2 times time, which is another t. What will this give us? Let us consider this. This is mLt. The one repeating again is t. This is t raised to the power minus 2 times another t. By virtue of implication, this means t raised to the power minus 2 means 1 over t times another t. Remember, this is still multiplied by this t. This is just like saying t over t times t. That's exactly what we have here. T over t times t. This t cancels one of this t. All we will have left will be 1 over t, which means here we're going to have t raised to the power minus 1. In another way of breaking this, t minus this can easily be said to be t raised to the power. The power of this is minus 2. The power of this is 1, because anything raised to the power 1 is itself. So this is just like saying minus t. Since multiplication is involved from multiplication law of indices, the bases are the same. We will just simply add the powers. Minus 2 plus 1 will give me t raised to the power minus 2 plus 1 will give me minus 1. Automatically, it is still the same thing I'm talking about. So we notice that the power here of t here becomes minus 1. So this will give us mLt raised to the power minus 1 as the dimension of what? Impulse, as the dimension of impulse. Okay, Tokyo is the last example in this row. The 10th one is Tokyo. What do you mean by Tokyo? Tokyo is the moment of a couple. Tokyo is the moment of a couple. In other words, Tokyo is what? Force of the couple times the distance covered by the forces, which is one of the force times the distance. Force is expressed in mLT raised to power minus 2 times the distance, which is expressed as what? L. Dimensionally, Tokyo will be expressed as m. L times this L becomes L squared, then T raised to power minus 2. This happens to be the dimension of Tokyo. This happens to be the what? The dimension of Tokyo. Okay? Having said all this, as part of the examples, numerous other examples, so with this, it can serve as the basis for you to work on any other example, any other question given to you. Just the derivation, use it and get the dimension analysis. Now, how do we use dimension analysis to prove or validate formulas or determine whether a formula is correct or not? Let us look at the way of using dimension analysis to prove the plausibility or the validity of a given equation in physics. Of a given equation in physics. Look at a question like this. By dimension analysis, this is one of the equations of uniformly accelerated motion. V is equal to U plus 8. By means of dimension analysis, we can prove whether this formula is valid or not, whether this formula is true or not. We can still take more examples to that effect. Now, how do we do this? We say what we want to prove is this formula V is equal to U plus 8T. First of all, when you have a situation like this, express everything in dimension. First of all, express everything dimensionally. So, expressing all in dimension, we are going to have V is velocity. Remember, in this question, they will always attach it where all the symbols have their usual meaning. V here is velocity. Dimensionally, velocity is expressed as LT raised to power minus 1, which is equal to, this is initial velocity, final velocity, which is also LT raised to power minus 1, plus acceleration is LT raised to power minus 2 times time, which is another t. Breaking this down, we have LT raised to power minus 1 equal to LT raised to power minus 1 plus LT raised to power minus 2 times t will give me t raised to power minus 1. If this is so, I have LT raised to power minus 1 equal to LT raised to power minus 1 plus LT raised to power minus 1 is just like asking us, assuming all this LT raised to power minus 1 is s. What will this be? It will also be what? S. S plus S will give me 2s. The same way, LT raised to power minus 1 plus LT raised to power minus 1 will give me 2LT raised to power minus 1. Since 2 is a constant, we can literally say that LT raised to power minus 1 is equal to LT raised to power minus 1. Hence, the formula is valid. Hence, it is a valid formula because at the end of the day, the left-hand side of the equation has the same dimension as the right-hand side of the equation. LT raised to power minus 1 is equal to LT raised to power minus 1, ignoring the constant. This is a constant, not a dimensional parameter in the equation. Since it's not a dimensional parameter, it's a constant, it will be ignored. LT raised to power minus 1 is now equal to LT raised to power minus 1. Therefore, the equation or the formula or the expression is plausible, is sensible, is valid. It's valid. Okay, let us prove another one. Let's see whether this is whether the expression above is valid. F is equal to mv squared over t. Mv squared over t. F is equal to mv squared over t. F is equal to mv squared over t. We want to prove this dimensionally. What do we do here? First of all, in any case, whatever, anytime it's being given to you, no matter the question, first of all, express everything in dimension. That's the first step. Express everything in dimension. So expressing in dimension, we're going to have that force is mLt raised to power minus 2, which will be equal to mass is m, velocity is Lt raised to power minus 1. Remember, all is now squared, divided by t again, which is what? As dimension like this. So this will give me mLt raised to power minus 2 equal to m. This will give me L times this will give me L squared, Abby. This is t raised to power minus 1 times 2 give me minus 2, all divided by t. This will give me that mLt raised to power minus 2 equal to m, since there is no other m, L is here, L squared, t minus 2 divided by another t will give me t raised to power minus 3. Now, mLt raised to power minus 3 is not equal to mL squared t raised to power minus 2. Therefore, the expression is invalid. This expression is what? It's not valid, provided that the dimension of the left-hand side is not equal to the dimension of the right-hand side. The dimension of the left-hand side is not equal to the dimension of the right-hand side. Finally, let's take another one of the equations of motion again, and still find out whether the equation of motion is actually correct or not. So by dimensional analysis, show that h is equal to ut plus half at squared. By dimensional analysis, show that h is equal to ut plus half at squared. First of all, bring down this. H is equal to ut plus half at squared. Dimensionally, express everything in dimension. Expressing all in dimension. What are we going to have? H is a distance. Remember, in this case, all the formulas, all the symbols have their usual meaning. All the symbols have their usual meaning. Expressing all in dimension. This is height, which is in distance, which is length. Dimensionally, height there is expressed in length. This is initial velocity, which is Lt raised to power minus 1. This is times this time, which is another t. This is ut. This is ut. Then plus half times a. Acceleration is Lt raised to power minus 2. Time here is t raised to power what? 2. Let us break all this down. This will give us L being equal to L t raised to power minus 1 times t raised to power minus 1. We cancel out. It's just like saying t over t. To cancel out and give you 1, which is just like saying t raised to power minus 1 times t. Which is raised to power 1. Minus 1 plus 1 will give you 0. Anything raised to power 0 is 1. So here, t raised to power minus 1 times this will give me 1. Anything raised to power 0 is 1. Because the power will give you 1 minus 1 plus 1, which will give you 0. So t raised to power 0 gives you 1. Okay? Plus half into L. T raised to power minus 2 plus t raised to power 2 will still give us 1. Because we are going to have minus 2 plus 2. And minus 2 plus 2 will give us 0. T raised to power 0. Anything raised to power 0 will give us 1 from 0 law of indices. Okay, having said this, that means L is equal to L times 1 is L plus half L. This will give us that L becomes equal to L plus half L is L over 2. Expressing this fraction, expressing this fraction, we are going to have, if we express this fraction, we are going to have, this is just like over 1. LCM of 2 and 1 will give me 2. 2 divides 1 will give 2. 2 times L is 2L, plus 2 divides 2 will give me 1. 1 times L will give me L. If you don't want to work it this way, simply multiply both sides, every term by the word LCM. Multiply all the terms by the LCM. The LCM of this and this is 2. These 2 are multiplied everything. I think that should be the easiest way for you. This is what we have. The LCM of this, the 2 and 1, this is just like 1 here. The LCM of 2 and 1 is 2. So multiply by the LCM. Multiply all terms by LCM, which is what? 2. Which means we are going to have L multiplied by 2 will be equal to L multiplied by 2 plus L over 2 multiplied by 2. And this will give me 2L equal to 2L plus 2 cancels 2, L, which means 2L will be equal to 2L plus L will give me 3L. If this is so, that means if I divide both sides by the coefficient of this, L becomes equal to 3L over 2. Therefore, L becomes 3 over 2L. So, since 3 over 2 is a constant, we can now say that L is equal to L. Hence, the expression is what? Valid. Hence, the expression is valid. It is valid because the left-hand side is dimensionally equal to the right-hand side of the equation. Provided that the left-hand side of the equation is dimensionally equal to the right-hand side of the equation, the expression is dimensionally correct. You meet me here again some other time. Still remaining a humble, right.